So the afternoon sessions are going to be a little bit different. There'll be talks which will be perhaps a mixture of methodology and applications, but tend to be focused on a particular application area. So our first talk this afternoon is by Bertrand Iooss, and he's going to be talking about circuit quantification from industrial applications.
Thank you, Dave, and thank you for the invitation. So I will try to give some motivating applications in my area and in my company. My company is called EDF, which is Electricité de France. And to begin, I just want to explain what we do in this company. This is the big company of electricity production and distribution systems of electricity also, of course. And indeed, in the context of electricity production, we have many uncertainties. So just to start, I give a few examples of what kind of facilities we try to exploit. Hydraulic dams, I don't know the number, but a lot, of course. I know the number of nuclear power plants, which is 58 in France. Some wind systems and solar energy, etc. And the uncertainty which arise in this energy production system are numerous. First, we can talk about hazards about the demand of electricity, about the weather, which has a strong impact on the electricity productions. The incomplete system knowledge of what we do when, for example, we make some nuclear reactions in a reactor. The aging, the physics, which is not perfectly known. Of course, there can happen in this industrial facility some failures that we have to understand and to predict, to try to model, and also the context of external aggressions that we have to take into account in order to operate the facilities, earthquake, river flood, etc., etc. So in order to better understand, EDF has a big research and development divisions of 2,000 people around, approximately. And a lot of these researchers develop some numerical simulation codes to be able to simulate what can happen in its systems. For example, we can try to simulate the failure of the dam, and as explained this morning, we try to simulate the behavior of nuclear reactor from the fuel consumption to some potential accident management, to some here the electricity production phenomenon, and the refreshment of the hot water, etc., etc. So we are a lot concerned by the computer experiments domains, and this is the goal of the team where I worked. It's a team of about 15 people on the research and development divisions, and the main topics, our main topics, is to develop and to use statistical tools for the risk management. Of course, sometimes we analyze some systems where we have some failures. For example, when we study the lifetime of a pump, we have a lot of what we call some experiments, a lot of years of experiments, and we can apply some statistical tools. We can try to apply the classical statistics and machine learning techniques to understand the behavior of this kind of failures. In some other context, we have a very small database of system failures, and so we can deal with other tools like Bayesian statistics, or we can try to use simple probabilistic tools like concentration inequalities in order to qualify the systems and in order to compute some probability of failure. But I am mainly concerned with these situations when we have no observed failure, but we have to prove the safety. of course, it's very important. And in this case, we deal with we develop physical models, and so we talk about simulation uncertainty. Alors, there are many things to say, but I will try to simplify just to give an idea of what research engineers like me try to do. So the context is the one of using best estimate. Best estimate is a word that we use mainly, I think, in nuclear engineering. Best estimate computer code is the fidelity, a computer code which is high fidelity, but which can be used in an engineering context. This is not the highest fidelity of physics, but we can use this kind of computer code. And I can simplify by talking about three main objectives, three main studies. We can talk about a research and development study, saying that we try to use the physics to understand a phenomenon, because the fuel system is not completely understood, but we know the essential phenomena. Okay, and so we use these computer codes to make what I call exploratory studies. Another context is the context of safety studies. These are regulatory studies where we have to compute, we have to prove that the risk is below a threshold, and we want to compute this failure risk. So we can want to compute some probability of failure, some quantiles, high-level quantiles, and it's important to also make the link between this risk and the variables and the phenomena that we want to take into account in order to prioritize the risk indicators. Last, what I call design studies is that when we want to optimize a system, we want to optimize the performance of the system by finding the best configuration of the parameters of the process. Okay, again with a simplified view. So we have uncertainties on inputs, which can be of different kind. We have at the center of the process our physics. It can be an experiment. It can be experiments, but here I will talk about computer code. Okay, with here I P inputs and the output Y, and we deal with a probabilistic point of view. We can be interested by computing all the distribution probability, or all the probability distribution of the output. We can want sometimes just the probability that the output exceeds a threshold. We can want just to estimate a quantile. There are many different situations. Okay, excuse me. So as said this morning, the two key points from a methodological point of view is how to choose the experiments that we run, and possibly we will need some statistical techniques, some mathematical model to obtain this kind of things. Just here I would like to talk about also several things. One of the goals can be a goal of safety acceptance, and in this case the very important word is the VVUQ. We have, of course, to prove that our computer model is validated, is verified in terms of numerical analysis, and we have to give a result with some uncertainties that has to be qualified also. Okay. Another thing is when we want to make some performance gain here I will talk about the classical DACE view, design analysis and modeling of experiments. And finally, more generally the importance of, and I will talk about this after, the importance of disseminating good practice of statistics to the end users. We can do all the works in my company, so we have to develop some very rigorous and clear methodology to be used by the engineers who don't have the time to read the papers, to understand completely the mathematics, but we have to give them some robust tools that can be applied in an industrial way. Okay? Just here, to precise the context, EDF want to develop some open source softwares. It's important to say this because the software we use have to be validated by independent organization. So the open source view is important to show to everybody what are in our software. So here I give just a few software. This is Telemac, which is a software of hydraulic, with hydraulics. Aster is a software with mechanics. We have also software like Saturn, which is for computational fluid dynamics. Salome is a big software for coupling the elementary software. And in terms of uncertainty quantification, we developed the open source software which is called OpenTurns, and I have a slide about it just after. So in my talk, I will try to give some examples. It's not, I will not detail the mathematics, but I will try, maybe I will not succeed, but I will try, to give the sense of what we do. I start by two examples of applicative projects. Projects can be the projects on several years, for example, 3, 4, 5 years, to develop a new methodology and to put it in production. And after, in a second time, I will give a few research issues that we have detected as important on the subject of sensitivity analysis, because mainly the basic tools are insufficient, because in real world sometimes, or very often, things are more complex than just the basic methods. Okay? So the first example is about river flood risk example, and I can introduce with this example some visualization issues. Visualization is important for engineers. It's very important to give them some graphical tools, because we want they use it. And after, I have a second example about non-destructive control process qualification. Okay, so in this project, we want to apply directly what we call the generic uncertainty quantification methodology. So not new in this figure, but this picture allows just to fix the main steps in a graphical way, the main steps that we need to be interested when we applied uncertainty quantification methodology. So we have divided in a few steps. So the first step is to specify our problem. We have a real system, and we have developed a numerical model. Okay, so here I put different kinds of parameters. D will be left out after. D is just to say that we fix a scenario when we make a study. We have to fix some things, and these are the fixed parameters. And all we do after is conditionally to this scenario. Okay, x are the environmental variables, and theta are the physical parameters that we can maybe, if we have some data, that we will try to calibrate. Okay. Once we have said this, we have defined the inputs. We have to define what we call the variable of interest, the output of the numerical model, and important, the quantity of interest, which is in the probabilistic framework, which is the statistical quantity that we want to deal with. For example, we can be interested just by the variance of the output, so we will apply some technique, but we can be interested by a rare events context by computing the probability that the output exceed a given threshold, and the techniques will be different. Okay, the second step is to put some probability distribution function on our uncertain input, the x and the theta, of course. Okay, so if we have some data, we can apply this very simple statistical fitting tools, but sometimes we have, often we have no data, so we have to make some hypotheses, some bibliographic analysis, etc., some expert judgment inference, etc. Another important thing is to model the dependence between inputs, so we have chosen to use the copula formalism in this methodology. Okay. In the case we have some data, some observed variables from experiments, of course we try to calibrate what we want, so for example the theta parameters. Okay. So this is a step, what we call the uncertainty quantification of the inputs, and after the two other steps, propagation of the uncertainties and sensitivity analysis. So just a very simple picture, but which allow us to communicate to the end user in an easy way. Okay, so the open source software that we have developed, which is open source, as said before, have many techniques for each of these steps. Okay, we can deal with stochastic process. We have put the metamodel polynomial chaos and Gaussian process inside, and we can deal also with some optimization framework when we want to optimize, maybe with some uncertainty management. We want to optimize the variable of interest, well, etc. If you want more details, we can. I can explain it after. Okay, so in this first example, this is with another department, the department which is called Saint-Venant Laboratory. Saint-Venant because it deals with hydraulic of rivers. It's important for EDF to be able to predict the river flow, because we have some reactor on a river, so it's important to imagine the water level that can be reached. So we applied the uncertaintification methodology on this kind of event. So this is the Garonne River. Garonne is a river in France near Toulouse. Okay, and here you can see the name of some town. We can be interested by all the river ACE. The output of the model here is the river level. We have performed an uncertainty propagation step, and so in blue you have in this color you have the water level at each spatial location of the river. Okay, we can be interested by a specific town, here Marmande. Okay, and here I put the mean of the river level at this town in function of the number of simulation. Okay, so this is a very simple application. What is important to say is that, okay, we have a mean map and a standard deviation map in order to control the uncertainty at each spatial location. Okay, and this is the probability density functions in Marmande. Okay, so okay, it's interesting, but maybe with 70,000 simulation, in fact, we have obtained 70,000 maps, and we have just synthesized this information by giving the mean map and the standard deviation map. So we think that it can be statistics can bring more things than just 2 maps. So we have tried to study other things. To illustrate this, I give another example, which is the example of a thermal hydraulic accident inside a nuclear reactor. So imagine that here you have the cold water which arrives here, and the goal of the cold water is to refresh the fuel, and after it becomes hot water, and we have some exchanger to create electricity. Okay, so if we have a large break on the cold water, we will have a big problem, because the water level will decrease, and so the fuel temperature will increase. So we have to make some exercise on this, not real exercise, virtual exercise, to understand this accident. And here, for example, we have simulate this kind of accident. I have make 100 Monte Carlo sample. You see that I have 50 random inputs. Okay, it's many. And the output of each run is a curve. This is the temperature in function of the time. And with 100 Monte Carlo sample, I have 100 curves. And I would like to synthesize this information not only by the mean and the standard deviations. So we have tried to apply, and we'll show the details just after, the functional box plots to understand, to see if this tool is interesting in our context. Alors, functional box plot is just the extension of classical box plot for scalar variables to functional variables. Here the functional variable is discretized, but it's a function, in fact. It shows the temperature in as a function of the time. Okay, so we have tried to apply 2 techniques. I don't know if somebody knows them here. The technique of band depths. Band depths consist in computing the depth of each curve inside the noodle plate. We can call this a noodle plate, like this. Okay. Inside the ensemble of curves, and the curves which has the strongest depth can be called the central curve, and the curves which have a low depth are extreme curves. Well, there are many ways to compute this depth, this band depth. The simplest is the following: you take all the bands of the, you take all the combinatory of 2 curves, and for each curve you count the number of bands which includes the curve. Okay, no, more or less. And you divide by the number of possibility of choosing 2 curves among the n curves. Okay, so the higher is the band depth, the more central is the curve. And this kind of techniques which allow to build some box plot with here which contains this gray contains 50% of the curves. Here I contain 90% of the curves, and I illuminate the other curves which can be considered as extreme curves. maybe not as outliers because maybe they are very normal curves, but there are some extreme curves. Well, this is a first technique, and a second technique is to pass by dimension reduction of the functions, for example by some principal component analysis, and then in the reduced dimension space we make HDR. HDR is high density region, so we model the density, the density functions, the multivariate density functions in the reduced space. So in this paper they use only 2 components, and some colleagues have extended this technique to many 10, 15 components. So in terms of statistics it's not very complex, but it's important to detect this kind of tools, because it's better it's very interesting for the end users to be able to produce this kind of curves, and after it can take, for example, the blue curve. This is a very different curve than the others, and try to understand which combination of inputs have led to this particular behavior, which is, you see here, the temperature here is very high, for example, and etc. Okay. We have tried to extend these techniques to spatial support data. So here we have unidimensional functions, and now I have bidimensional functions. So this data comes from this paper. We have this is another example where we want to predict the contamination of radiologic of radionuclide, okay, on a site, okay, via hydrogeological calculation model. And we have made at this time 300 runs of the models, but we never analyzed all the 300 maps. We have just compute the mean map and the standard deviation map. So here we think that it's important to have an automatic tools which is allowed to detect the outlier map. Okay. So the band depth concepts consist in ordering the 300 spatial output maps and to obtain central maps and extreme maps. So we have made this. This is excuse me. This is the central map, which is the median. And so here I just put some example of central maps, and after you see that we can detect some very different maps with an automatic tool. So it's important also because with 300 or with 1000 simulations we cannot analyze this by hands. So this kind of tools is very useful to find this kind of map in an automatic way. We have not developed, there are many works to do for this kind of issue. I don't work anymore on this subject, but we have identified other techniques like contour analysis techniques, other challenge when we will have some 3D or 4D outputs. I work with some colleagues. We try to extract the topology of the result of a simulation. So I'm not a specialist, but trying to extract the topologic nature of a map can be useful. And another subject which is difficult is that in this case sometimes we cannot store all the results, all the simulation results. So we have to do what we called in the visualization community in situ analysis, but in the statistical community, this is more, I think it's called online analysis. We have to analyze the data when they arrive, but after we cannot store them. So I don't have the solutions to compute this kind of thing without storing the data, because when I compute the depth of the curve or the depth of the map, I need all the maps. So this is also, I think, a mathematical challenge to be able to do this online. Okay, well, I don't have any idea to do this. Okay, now I turn to sensitivity analysis. Alors, coming back to my river flood example, for the exercise, we have compute some maps of sensitivity indices. So this morning, Ralph explains the Sobol indices technique. So we are able to compute at each location where we predict the river level, we are able to compute the sensitivity indices. So this is the sensitivity indices for a particular input, and this is the sensitivity indices for another input. So we can see that this input is more influential than this one, and that the influence is larger in this zone than in this zone. So for the physicist, it's also interesting to be able to interpret, to have this information. Another thing to finish with the visualization part, maybe some of you know this kind of tools, which are some simple data analysis tools, but we try to exploit these classical tools of statistics for analyze the simulation results. So just to explain, here I have my scatter plot. This is my 4 inputs and my output. And this, in sensitivity analysis, this tool is called the cobweb plot. In data analysis context, this is called the parallel coordinate plot. Each vertical axis is a variable. So you have your 4 inputs here and the output here. The goal is to make a line for each joining each combination of the inputs and going to the value of the output, and after you illuminate a zone of the outputs, and this allows to visually see the influential inputs. For example, here the water level, the large values of water levels comes from small values of this variable, these variables, and large value of this one. This is the flow rate. So of course it's logic, and this is the friction coefficient of the river. Okay, and the ParaView software, which is developed by the company, Kitware, an American company. They developed this kind of platform to visualize data, make the link between the scatter plots and the cobweb plots. So, well, just to say that this kind of tools is very useful for end users. And when we developed, when we show them this kind of thing, of course, it creates a strong interactions with physicists, and we have succeeded to provide some interest of engineers and users by using these tools. Okay. Now in the ParaView software, we have tried to link this visualization software with our uncertainty quantification software, OpenTurns. We try to, in ParaView, to use some functionality of OpenTurns to make some uncertainty quantification analysis, to use the methods of uncertainty analysis useful to compute, for example, the functional box plots. Here, this has the functional box plots, and to link this kind of thing with the cobweb and the scatter plot. Bon. I will not detail this, but if you want, we have just written a paper here that I can send. Okay, a second example is more complex. This is an example about the qualification process of the performance qualification of non-destructive control process. So inside a reactor, you have what we call the steam generator. It's, I think, 20 meters, 8, maybe 30, I don't remember. And there are thousands of little tubes inside, tubes like this, okay? And these tubes allow to exchange the water with the vapor. Bon, okay. There are many constraints because the pressure is very, very high and the speed of the water is very high also. So these tubes vibrate, and so to block them, we put some kind of systems. In French, this is a bar anti-vibratoire, anti-vibratory bar, maybe. So it creates some defects, and with the years, of course, sometimes the defect is too large. You see, for example, here, maybe you see here the defect, and we have to block the tubes because it can fail. The tube can fail if the defect is too large. Okay, so to control this, we use some non-destructive process, which is a probe of eddy current, an eddy current probe. Okay, and with the signal of the probe, we can say if there is a defect or if there is no defect. Okay, because we cannot inspect visually, of course, in this place. So we can just put some probe and we try to see if there are some defects in each tube. Okay, so there are many engineers who works on this process, but the research and development researchers try to develop a software which simulates the non-destructive control process. The goal is to qualify a non-destructive control process, and so we want to compute to know their performance, and so to simulate this we have developed a software. So this is a software which simulates electromagnetic waves. When we pass the probes inside the tubes, they create electromagnetic waves, so we simulate electromagnetic waves. But of course there are many uncertainties. There are many parameters that we don't know the exact values in this kind of systems. The exact position of the bar, the exact permittivity of the material, we don't know this, etc., etc. So we want to qualify this non-destructive control process by using probability. And in this kind of things, the classical tool that we use is called the probability of detection curve. In the axis, you have the size of the defect, and here you have the probability that your probe, that your process detects the flow. So where the size of the defect is very small, you cannot detect it, and where it's very large, you are sure to detect it. But there is an intermediate region where we don't know. Okay, so we want to estimate this curve via with our computer model. The problem is that each run of the computer model is very, very costly. Okay, here I put yes, this is true, this is not fake. this is because it's not my company which makes the run. It's another company, and we have to pay them. And each run is cost 200 euros. I don't know how many in pounds. It's important to know what is the number. So we have chosen to use the metamodel techniques to construct this. Well, I have the full details after. But when you have this kind of things, it opens. It opens. In fact, new ideas and new research issues. For example, we can say usually that when we want to build a metamodels, you make the number of runs is 10 times the dimension. So here the dimension is 7 or 8, I don't remember. So we have said, okay, maybe 100 runs will be sufficient. But in fact, if 50 is sufficient, it's very important to know this. So what we have proposed to use is to use a space filling design, but with some sequential property. So at this stage, the only space filling designs with sequential properties that we know is the Monte Carlo design, but no, Monte Carlo is not space filling, rather quasi Monte Carlo design, like Sobol sequence or Alton sequence, that we know that these designs, there is an order of the simulation points in this kind of designs. Okay, so here we have used a Sobol sequence for the design, for the space filling design, but I think that this phase can be improved by imagine another things design, like a latent hypercube sampling maximin design, but with some sequential property. Sequentiality means that you have defined your design with a number of points, but if you take a sub-number of points, the first point, we have again some space filling properties. So this is another topics that I try to work with Luc Pronzato, but we haven't started to work on these topics. He has started, but not me. So you see this kind of industrial questions gives us new ideas, new development ideas, and finally very interesting scientific topics. Okay, so I will not. I will pass to this kind because this is not very interesting. Well, okay. For this kind of things, finally, the final product that we give to the engineers, because we work for the EDF engineers, we have to give them a methodology, a global methodology, and what we try to furnish is a progressive methodology, because sometimes, for some examples, things will be simple, and for some other things will be complex. So we start by giving them very basic and easily understandable methods based on simple linear models, but on some case, the hypotheses behind this kind of models are not valid, and we have to pass to other types of techniques like Gaussian process metamodel or polynomial chaos metamodels. So this is what I call a progressive methodology. We want that the engineers apply the simplest methodology adapted to their problem, bon, etc. Okay. Alors now I have 5 minutes to explain a few research issues on sensitivity analysis. Okay, alors sensitivity analysis globally understands the behavior of the model by decomposing input-output relations. I would like to distinguish 3 objectives. The screening. You have many input variables, and you want to find the ones that are non-influential and the ones that are potentially influential by qualitative techniques, maybe qualitative, a more quantitative objective where you want to precisely partition the variability of your outputs in function of the inputs, as a function of the inputs. And this is new, but it's very important for us. It's what I call robustness analysis. Because sometimes the safety authorities say us, okay, you do some things, but you are not sure about your probability density function, about what I call the input uncertainty laws. So when we compute a quantity of interest, maybe a quantile, we have to prove that the quantile we give is robust with respect to some uncertainty on the uncertainty. Sorry. After we will have the uncertainty of the uncertainty of the uncertainty, etc., etc. But it's very important in my engineering context. So I call this robustness analysis. Alors, I remember 8 years ago, I had only 4 issues in sensitivity analysis. So now I have more experience, and I have 8. Sorry, maybe in 10 years I will have 16, I think. But I think it's a good summary about all the issues we can find. Our first issue about the numerical model itself. The numerical model is complex, okay. Maybe, so you have to understand the interactions, the nonlinearity, maybe you have to find the discontinuity. It can be costly, several minutes to days to compute, and we know that in sensitivity analysis, global sensitivity analysis requires a lot of runs to compute sensitivity indices. So the metamodel techniques can be useful. Second kind of issues about the inputs, the dimensionality of the inputs. This is the main issues in sensitivity analysis. The dependence between inputs and the uncertainty on the uncertainty on input PDF. Okay. And finally, the 3 last are about the model outputs. When y is not a single scalar but a high-dimensional vector or a functions, so things are more complex, but we know how to do. And a new issue that I have explained before, when the outputs are too voluminous. And in this case, we cannot store the outputs. So here I have another work, and we call this iterative sensitivity analysis. So we compute sensitivity, we iteratively compute sensitivity indices without storing the results. In fact, we just applied update formula of the mean, the variance, and the covariance. It's not very complex. But in practice, it can be complex. And finally, when the quantity of interest is not the variance, but another thing, like a probability of failure or a quantile, here you have some works about goal-oriented sensitivity analysis. I have the reference if you want. So I have 1 minute, no, 0 minutes. So I will not talk about Shapley indices, which is a new proposition of Art-Owen. When you have some dependence, it goes beyond Sobol indexes by taking something which came from game theory. Very interesting, but I pass. And the robustness analysis, so this is some works we have developed with PhD students and with some colleagues from University of Toulouse, Fabrice Gambois. Just the principle. So I have explained that the problem is mainly the disagreement of the safety authority due to the lack of knowledge on the input PDF of the epistemic variable. And what we try to use, I'm not sure that they will be convinced, we will try to convince them, is what we call perturb the law-based indices. The idea is you compute your quantity of interest with some input probability density functions, and we find a way to perturb them, well, in a certain sense, with some notion of Kullback-Leibler divergence. We perturb them, and we compute with the new, with the perturbed density functions, we recompute the quantity of interest. And we define some sensitivity indices, which is the difference between the perturbed quantity of interest and the initial quantity of interest. The idea is to show that with some perturbation, for example, we perturb the mean for Gaussian variables, we just translate the Gaussian variables, or we perturb the variance for the Gaussian variables, we just flatten the distributions. Okay, we perturb the mean, and we see if the quantile or the probability of failure change a lot when we perturb this. So the result of this kind of pli, I don't know, is some curve. In abscissa, you have the degree of perturbation, and each curve is the perturbation of a particular input. So this is our current work, and we try to apply this on some thermal hydraulic simulation accident. So thank you very much for your attention, and I have all the reference here. And just if you want to look at this web page, a lot of information. This is a French research group on the computer experiments topics. Thank you very much.
Okay, questions or comments?
In one of your early slides about open terms, you made the distinction between the model and the real system. And you even had a function for the discrepancy. B is a function of x and d. Yes. What kind of function is that, and how do you quantify it?
So in the software, we don't have the techniques. We want to use the Kennedy and O'Hagan framework, so by putting a Gaussian process on this bias, and by inferring the hyperparameters of the Gaussian process. So we had some PhD students who have applied the methodology of Kennedy and O'Hagan, and who have tried to make advance on these subjects. But so we think that the choice of putting a Gaussian process can be very interesting, and we try to apply this on our industrial example.
Hi, I can't remember the name of the figure, but it was parallel something or other. Lots of lines.
Parallel coordinates.
Lots of lines.
That one, yeah. On this, you said that sort of large values of one were associated with small values of another, were associated with large values of another. Do you just mean that the bottom's been sort of not included in the red, the bottom half of the range on the right is not included in the red, or do you mean the line at the top there is associated with the bottom line of the second parameter? So are you just looking at where the ranges are now smaller, or are the lines actually related? That makes sense.
Excuse me, I didn't understand very well, but maybe.
So on the right hand side, only
Here? Oh, yeah.
that one, yeah. Parallel coordinates, sorry, that's the one. On the right hand side, you've only got red at the top.
Yes.
And on the second column, I think you said that low values of that were associated with high values of the right hand side one.
Yes, it's.
Do you mean that the lines are related in such a way that the top of the red and the last is associated with the bottom of the right, or do you just mean that the ranges are reduced? I just struggle to see
I'm
those
sorry,
sorts
because
of
I don't
relations.
understand very well the question because of my language difficulties. But no, sorry. I mean that when I illuminate all this so with my mouse, I take a range on this, and after it eliminates all the combination which arrives here, and after just visually I have to see if there are some more density of red on each line. So here I see a highest density of red for large values, and here more black density. Here I see highest red density for low values of these variables. And here, you see, maybe I didn't understand your question, I think.
That did answer the question, but I was just wondering if all your red was spread out in 2 dimensions, but actually all the reds at the top were related to the reds at the bottom,
yes.
You wouldn't be able to see that in this.
Okay, I'm sorry.
So if they were related such that if they were perfectly correlated, say, you wouldn't see that in this plot.
If they are perfectly correlated?
Yeah, if 2 inputs were perfectly correlated.
Okay, I understand. In this case, I have no correlation between inputs. So the question is, if some inputs are correlated, what happens?
They might not be correlated in terms of when you run your simulation, they're correlated, but when you constrain them, then they might become correlated. And you'd miss that in this plot, I think. So you might not.
No, the idea of this plot is just
range
not to understand the relation between the inputs. It's just to understand the relation of this axe with the others.
But if 2 of them were perfectly correlated, you wouldn't see a reduction in the range necessarily at all.
Yes, you are right.
I wonder, are there any plots in this software that you
But
see
in
that?
this case, if two inputs are perfectly correlated, this is the question?
If they're perfectly correlated by the time you've constrained, you might not see any marginal uncertainty reduction at all.
But I don't put 2 inputs perfectly correlated. If two inputs are perfectly correlated, it's just 1 input. No?
I'll talk to you after.
Offline. Any other questions? Okay, let's thank Bertrand again.
Thank you.